Okay, so today we have the closing lecture, and I have the duty of introducing Professor Carlo Rubbia, which I think doesn't need any introduction, and especially for physicists at CERN like me, it's really, really an honor to be here introducing. I mean, Professor Rubbia was linked to CERN since the beginning. He's one of the driving forces, and it is in the last decades of particle physics one of the reference person, one of the reference physicists. Clearly, since the beginning of CERN, he was involved in all the programs, especially for electroweak physics studies, that led at the very end to the proposal and also the discovery, the proposal of the experiments and the discovery of the W and Z bosons, for which he shared the Nobel Prize in 1984 with Simon van der Meer. And then he continued on in this, and he was one of the driving forces in pushing and shaping CERN as it is now, and especially the LHC as Director General here at CERN. He continued on. The intellectual range is really, really diverse. I cannot really go through everything. Just to tell you one thing, in the last few years, he devoted his attention to some fundamental humanity problem, which is renewable energy and how to basically build up new power plant with renewable energy. And it is not only a theoretical study because, as we speak, his ideas are put actually in function in many of these new generation solar power plant in many places in the world. Still, he continued to be a leading person in high-energy particle physics, especially in the search for dark matter and all the experiments, and he agreed actually to share with us some of his thoughts concerning this topic. And I think I already took too much time.
Thank you.
I leave the grounds to
fine.
Professor
Right.
Rubbia.
Thank you very much. Okay, ladies and gentlemen, I will be spending about an hour telling to you about an incredibly exciting new situation which is developing today, which has to do with the so-called dark matter. Well, I'll explain to you what the dark matter is, why do we think dark matter is there, and we're going to tell you what it is important to do in order to transform dark matter, which is presently a complete mystery, into something which can represent a part of the world in which we live and in which we know. And of course, this is something which is definitely a very vast program. It requires both astronomy and elementary particle physics. In fact, now we are talking about an intermediate situation, which is called the so-called astroparticle physics, which includes one and the other. I have to tell you that these are truly exciting times, and you people which are now coming into this field of physics as beginners for the future of your existence will certainly find the dark matter is going to be one of the major questions that you're going to have ahead, and hopefully that you will be able to solve, because it will take a certain amount of time before these phenomena are really understood as well as we understood, for instance, 15 or 20 years ago, the Standard Model and other things that you know very well about. So let me start essentially by talking about from optical astronomy to elementary particle physics. Luminous matter accounts only for a tiny fraction of the total mass density of the universe, and only for 1/10 of the ordinary matter, namely baryons. While stars are very interesting and pretty to look at, and without them, astronomy would be astronomy, and we wouldn't exist ourselves, they represent a tiny fraction of the cosmic mass budget, about only 0.5% of the total energy and mass of the universe. As we have known for several decades, the bulk of the constituents of the universe are dark and only indirectly observable through their induced effects. In order to know more, the scientific activity of optical astronomy needs to be extended in a variety of ways. Particle physics provides an attractive solution, for instance, with accelerator experiments on a Standard Model and beyond. That is, we are here just at CERN, which is the place where most of these things are being done. A non-accelerator experiment, which may shed further light, for instance, on relic elementary particles left over from the Big Bang, in sufficient numbers to account for a significant fraction of the critical density of the universe. The earliest optical event, the CBR, has occurred 300,000 years after the Big Bang. The famous Kobe event, in which you see the picture of the universe, baby universe just being born, this round, very nice sphere which everybody of you are supposed to have seen, has occurred quite late in history of the universe, 300,000 years. But a large amount of facts had occurred before them. They can be evaluated today, recreating the phenomena with high energy collisions. This is what we're here for. In fact, the point is that the earliest visible image we have, the oldest image of the universe, as I said, is optical image, is only 300,000 years ago. Now, of course, we have the standard model, Saga, which is a well-known situation, in which is represented here, you know very well, there are quarks, there are leptons, there are bosons. The bosons are responsible for the force carriers. There is an element still to be confirmed, which is the Higgs boson down below in this picture. And all that, the universe emerged from an explosion in a vacuum, which occurred 13.7 billion years ago. This by now we know. And after 10 to minus 12 seconds, electromagnetism separated from the weak nuclear force. So weak interaction went one way, electromagnetics went the other. Z, W, and gamma were separated 10 to minus 12 seconds. Hot quark gluon plasma and leptons at the time were dominant. And then 10 to the minus 6 seconds after the Big Bang, hadrons are formed. And 103 seconds, lepton, anti-lepton annihilate. And between 3 and 20 minutes, the famous 3 minutes of the famous book by Steve Weinberg, protons and neutrons began to combine and start to form atomic nuclear. This is the Big Bang nucleosynthesis, which is in fact the reason why we are what we are today. The LHC to present moment is getting down to about 10 to the minus 12 seconds. This is the area where we are. The Kobe event is 300,000 years after this time. In between, there's a lot of things happening. One of the key elements of the history of the early times of the Big Bang time is the nucleosynthesis. The nucleosynthesis has now become, since recent years, an experimental science and precise science. Today we can do things and decide on these things, not only just by looking in the past, but seeing the effects of them in the present. And in particular, the value of nucleosynthesis now is extremely well understood. You can see here reasons which are, you look at the various elements, lithium, helium, deuterium, and so forth, and helium-4, and you are looking for areas within the universe where there is no activity occurred over the 13 billion years. So there is some leftover parts which are not being affected. For instance, if you go to a star, you will discover that the star is going to burn and modify the mass of the elements. But there are some areas in which things stay as they were at the beginning. And in those areas, we can look at those things, and we can try to estimate, studying today's nuclear physics, nuclear reactions, what happened at that time. Nuclear physics is doing a very excellent job today because, for instance, we understand extremely well what a star is doing, any star is doing today. We understand the supernova explosion like it would have been observed experimentally by us. We also understand the Big Bang nucleosynthesis, which is the initial formation of the various elements. And all these elements are characterized by one number, by the number here, which is this is a green light which you see there, which is a free parameter. And you can see that those are the numbers which you observed, and these are the possibilities represented by nuclear physics. And this represents, so to speak, how long nucleosynthesis has been burning. The more time goes by, the more this line will move this way, and more elaborate elements will get produced. The shorter is the time during which nucleosynthesis is burned, the less elements will be developed, and more primitive situation you're going to deal with. So all these numbers, all these very large numbers, are really characterized by one common value, which give us a certain intensity, if you like, of the Big Bang nucleosynthesis, and which is now a very well precise number within a very good and understood situation. And in fact, the evidence, the conclusion is that we can measure now the nucleosynthesis to about a precision about 10%. And now the value omega b and n is in units in which the total density in a dimensionless unit is equal to such a relative number, which is a small number, and which leaves plenty of room and possibility for other phenomena which occur. And as I said here, baryonic matter, ordinary matter, is generated by nucleosynthesis. It's not the dominant form of the matter of the universe. We know that extremely well. Let me skip that, and because it's a bit too complicated for the present discussion. Let me stay to here and reach essentially the conclusion. Looking at the situation which we have now from the Big Bang development, we can see that in fact the amount of dark matter, the present matter is only the little bit here. This is ordinary matter. That we are dealing with a very large amount of dark matter and a very large amount of dark energy, which are completely unknown to us. They're not visible. They're just, as now I'll explain you very briefly why they're there. The sum of all those things gives a value, critical density of 1. Omega total is 1, so this is something which has a lot of theoretical significance. And there is essentially only 4% of the universe, as I said, is done by ordinary matter, inanimate and living, of which we are made of and which we perceive. The remaining 96 is invisible and so far completely unknown. Now, this, of course, is an immense experimental result of immense experimental consequence. Today, with so much we do in physics, we still have no idea whatsoever. You have no idea. I don't have any idea about 96 of the stuff which creates our universe. It is absolutely a challenge to everybody who has to continue and to study those things and see whether you or we will be able to tell what is the truth about the greatest majority of energy, which is matter and energy right here. And all we know, standard model and everything else, is only this. Okay. Now, let me try to explain you very briefly why do we say that we have such dark matter. Of course, there are arguments of various types, but there are very simple experimental information. The simplest information is coming essentially from a galaxies, from any galaxy, for our galaxies, which are, of course, is a spiral object, as everybody knows very well. And in this, if you look at the dynamics of this system and you assume the matter is represented by the stars, gravitational force is around, you can extrapolate, you can use Newton technology to calculate what is the basic dynamics of a galaxy. As you know, the Newton dynamics is perfectly good for the solar system. We can calculate the movement of the planets with incredible precision. We can calculate the movement of the satellites, space programs, all kinds of phenomena which occur at the level of our solar system is extremely well known. If you make one step forward, if we go from a single solar system to the galaxy, we are in front of a disaster situation. And disaster situation is demonstrated by the following consideration, by the fact that the distribution of as a function of the radius, this is the radius from the center of the galaxy, and this is the velocity of rotation. Now, as you know, in an ordinary solar system, stars, planets which are very close to the sun are moving very rapidly. Planets which are far from the sun move very slowly because of the characteristic 1 over r squared of the Newton force. The situation here is totally different. You can see a velocity of a galaxy, and you can see that the speed of the galaxy is essentially a value which is constant. Instead of going down, like you would do in the case of the disk, is constant. So This is totally in disagreement to what you expect from putting a bunch of objects there. And by seeing the amount of light, from the amount of light you see around the galaxy, you can tell how many stars you have, and therefore how much mass. Well, then you get something which disagrees completely with the experiment. And obviously, there are two solutions ahead of you. One possibility will be to say that after all, well, as I say, we observe velocity as a function of r, and then we find that the movement is v is constant. That means the mass is becoming bigger and bigger the further we go from the center. So this is full of something else in there, which explains this phenomenon. And this, of course, is only, there are two solutions ahead of you. One, you can say, Newton dynamics, it only works for the sun, it doesn't work for a galaxy. Just throw it away. And then, of course, you can do anything you want. The second possibility, you say, Newton dynamics is correct, because after all, it's Einstein equations, general relativity, whatever you want, if you have no alternative to it. And then in this case, if you want to explain why you're getting that, you have to simply say that the matter we see here is not everything. There is something else in there, which is the gravitational values, with gravitational strength, which modifies the movement of the galaxy as a whole. But it is what we call dark matter, because we don't see it. So there is one very simple statement, major disagreement with the naive Kepler law of a thing which is perfectly obvious and not as big as you may think, which is a galaxy, our galaxy, most of the spiral galaxy in the universe. Now, a second problem comes from another indication, which is a phenomenon which is very vastly used in cosmology, which is the so-called gravitational lensing. What happens here, you have a detector here, which looks at a very distant star down there. And between the distant star and you, there is the object under observation, which could be a galaxy, could be a complicated structure of any type. Then you know that gravitational forces bend the light, and therefore, when this object is introduced between the source and the observation, you observe a focusing effect. The light is concentrated further. So more light comes here. It's like you have a lens here. It's a gravitational lens, which is produced by the presence of the material. Now, this gravitational lens, obviously proportional to the amount of material you have there, the heavier the thing is, the stronger is the gravitational lens, is a measure of the total mass you have in between. And therefore, by looking at these things, you can determine accurately what is those things by the help of this distant star, which is there to provide us with the kind of intermittent information. Now, let me show you in practice what comes out when, for instance, a distant star is crossed in between by one of those galaxies, and there is a gravitational effect. You can see at the time, you look at a very distant star, and then you observe the intensity of this light as a function of time. When another heavy galaxy develops in between, the focusing effect is increasing the amount of light which you observe, because the lens is in action, and you see a peak in the light. The size of this peak, the amplitude of this peak, is the measure of the mass which is producing the phenomenon. And it is interesting because you see the blue and the red, all the two very different surfaces, have exactly the same behavior, because this is light, is valid for every form of light. It's not a specific thing associated with certain spectra. It's not just the total amount of light, which remains as it is, but it gets focused by the presence of the lensing. And this is the so-called gravitational lensing, which is a tool which is extremely powerful to study that. Gravitational mass of the galaxy is measured from the focusing effect produced by a distant passing star. And you can see there where it is the line of the effect. And this is the focusing of the gravitational lensing. Now, we can have many, many phenomena of this, but let me show you one example which is an evidence for the dark matter. And this is a picture of a very strong collision between two galaxies. Two galaxies are just compenetrating each other, they're hitting each other, and making a tremendous mess of creating a system in which one galaxy is interacting strongly with the other galaxy. And you can see here the picture, you can see two things in this picture. Let me show you more clearly what that is. You can see here the visible plus stars, what you see, for instance, the light of your equivalent of the example of the galaxy I said you before. This is visible plasma. And those are the stars which are there. And then we can also observe gravitational lensing. We can also look at the matter present there. And so if we look at the gravitational lensing effect, we can observe also the same image, look through the effect of gravitational lensing as I described you before. And what you find here, that the gravitational lensing is one thing, you see here and there, and the stars are the other. And these two things are entirely separated. In this particular collision, the dark matter has gone one way, and the ordinary matter has gone the other way. They are separated by a very large distance, which is the intergalactic system. And this is a evidence, experimental real-time evidence, that we have a large amount of matter here, which is not visible, which is very heavy but is not visible, and which produces this gravitational lensing effect. The gravitational potential does not trace the plasma distribution, the dominant baryonic mass component, the majority of the matter in the system, as you can see from this line here and that line there, is unseen. And by now, we have at least 4 examples in the last few years have been observed of that. So we have a reality. We can observe many examples of a situation in which when our galaxy has these, they get shaken out or destroyed by some kind of major collision, then the two things are really moving as an independent devices, independent effects. And this is, in a sense, is certainly one of the major experimental evidences that, in fact, we are dealing with dark matter. Now, of course, this all happens in the stars. This is all gravitational phenomena. What we really want to do is to do an experiment in the laboratory. Remember, for instance, 250 years ago, the speed of light was measured first astronomically by looking at the movement of the satellites of the big planets and found there was some time shifts, but it was indicated there, it was even the mass was measured, but only when Foucault and Fizeau measured the speed of light in the laboratory that we really could understand that the light had a speed. Likewise here, we have the need to determine whether this dark mass, which should traverse us, it traverses the whole galaxy, is going to traverse us as well. And now what this thing is doing and how it's developing, and so what kind of effects we can come with. Now, as I said, so far, we have learned that all the dark mass effects have been of gravitational nature. And they obviously, we have other possibilities of explaining this, and now elementary particle physics may provide an attractive solution. The non-baryonic dark matter problem, relic elementary particle left over from the Big Bang. They could do that. Now, long-lived or stable particle with very weak interactions can remain from the earliest moment of particle democracy in sufficient numbers to account for a significant fraction of the critical density. It's what we've seen in the previous picture is just that. Dark matter must have participated in the evolution of the universe, presumably in comparable but different way than ordinary matter. Indeed, the dark matter has been the main driving force through its evolution. It's dark matter because of its mass, because of its things, which controls the movement of the universe as a whole. We are under the control, under the influence of movements which are presumably driven by the dark part of the story, and we are just following up with our 4% of the total, what the rest, 96%, is doing. The experimental search in the laboratory for new forms of matter outside the standard model is an extremely exciting problem. It has to be outside the standard model because the standard model gives nucleosynthesis, gives facts that we already know very well. But there is 96% of stuff which is outside the standard model, which we have to understand. Now, the key question is of which kind of interaction will be connected to dark matter. And the question is whether the dark matter is only gravitationally bound. If it's only gravitationally bound, we will never be able to do anything. It will be traversing us, it will carry mass, it will modify the way in which the movement of the planets go, or the galaxies go, but we will not get anything practical. If the dark matter, however, has some electroweak coupling with ordinary matter, then we have a chance to see some interaction of dark matter against ordinary matter, because W's and Z particles, for instance, are being exchanged between dark matter and ordinary matter in some kind of a way, and this can give us some events. That is, of course, created a very large number of alternatives. Theorists are very prolific in this thing. I said they have very fervent imagination, and they've invented a whole list of possible reasons why this dark matter, which, as I said, now is a physical reality, is in fact related to elementary particle physics. You have a whole line of things and many more coming. And of course, the question is, of course, nature may have decided otherwise. Some of these bets are more popular than some others. Some of these bets have more consideration than some others, but of course, we don't really know what the answer is. Now, one possibility is to connect these things with SUSY. SUSY, as you know, are supersymmetric particles, which are going to be presumably the next step for the LHC. And therefore, to say the LHC is, in fact, also going to produce the lightest SUSY particle and the neutralino. And this object may be stable for some reason. We'll discuss that in a minute. Why? And therefore, as the collisions in the colliders produce every possible particle, provided there is enough energy to make them, if you have a LHC, which is the largest possible energy available, you have the largest possible chance to produce even those heavy objects, which are just dark matter particles. So if we work hard enough with LHC, and if this thing is connected to electroweak interaction, if there's SUSY, for instance, there, sooner or later you're going to find something which will be the production of some new dark matter produced artificially by collision between protons for instance, in the LHC. So LHC is a perfect window to look for some of these solutions. This is, in fact, the solution to the neutralino. The other possibility is to say some exotic forms of massive neutrinos, like, for instance, this case here, and more generally, events which are, in fact, relic in nature, which are coming if there is so much dark matter around. There could be also reasonable possibility they want to design a detector which can catch a small fraction of this matter, for instance, depending, of course, on what is the nature of it. And, for instance, stellar neutrinos, neutrinos, and all kinds of things are another possibility of this this is Fermi imagination. But it is important to tell you that it is not a necessity. Other forms, and even classical fields, with purely gravitational effects may be amongst the possible alternatives. So we have absolutely no idea what makes this 94% of the mass of our universe. No idea whatsoever. It could be a classic field, it can be quantum mechanical, it can be coupled with electroweak, it can also be gravitational, you name it. In principle, all possibilities are open, these plus many more. And of course, the experiment may be able to tell us what is the right choice. Now, as I said, it's not only dark matter, but it's also dark energy there. I have no time to give you a very careful definition of the difference between dark matter and dark energy. But, I mean, at the present moment, we think dark matter is one thing, and dark energy is another. And the question is, may well be that dark matter and dark energy are, in fact, the same common practical origin. So nothing is known. It's all there for you to be discovered. Now, let's come to therefore, to a second question, is what about the dark matter from SUSY? Now, the point of this situation is a story which came up with a previous CERN accelerator, which is LEP. And here we have you know that the coupling constants are running. In other words, when you go up in the mass of the process, you find that the coupling constants of the various three basic strong electromagnetic weak interactions are in fact running. They move towards, in a logarithmic paper, towards the common line. And if you take just ordinary, this is the region of LEP, this is over where LEP is measured. And if you extrapolate these lines to something, saying there is a common line for all these phenomena in which electric weak interactions and strong interactions will somehow converge to something, you'll find there is no convergence whatsoever. You find that this line here and that line there, they just cross apparently in a remarkable situation. And there is no attempt to converge into anything significant to very large masses. So this is a reality, is a necessity. However, if we put in SUSY, if we introduce supersymmetric particle, say at the edge of LHC, at the edge of LEP, then also supersymmetric particles, when they come in, they will contribute to the running constant. And therefore, the running coupling constant, it gets modified by the presence of these supersymmetric particles if and when they become real. And therefore, we have a remarkable change in angle determined by the properties of the supersymmetric particle, which you can see move this line a little bit when this supersymmetric particle gets turned on. And you see another very remarkable result. With that, the three lines converge in one point. So if you have supersymmetry, then you can say that the weak, the strong, and electromagnetic interactions somehow are a part of a common story. And the common story will lead us to getting into a common, very high, common primary interaction, very, very high masses, which is right there. This has nothing to do with dark matter, but I mean, it is a part. If dark matter is related to SUSY, that's a consequence of that. And in fact, we have a possibility of a grand unified position with eventually another very nice experiment which can be done, which is a proton decay. Now, of course, the doubling of the elementary particle occurring at the LHC, the so-called no-failure theorem that many theorists have pretended to be there, has been widely supported by the theoretical physics community. And, of course, a low-mass Higgs is predicted as a precursory to the existence of SUSY particles, and all that will become a real blessing for LHC. You're going to find the elementary Higgs. The elementary Higgs will stabilize the way in which particles behave, and therefore it's a necessity for the SUSY. SUSY is the necessity for getting a credible story on the Higgs. And then you get this object, and this thing will work in a very reasonable. So everything is circumstantial evidence, but there are many things to make you think that indeed we are doing a very good job. Now, the next question now here is to know whether dark matter and SUSY matter are in fact related, because the purpose of my talk today is to tell you about dark matter. And the relationship between dark matter and SUSY matter is not far from being immediate. They could have supersymmetric particles by the dozen and still not having anything which can tell you about dark matter. You can have dark matter perfectly there and no SUSY at all, as another possibility. Now, obviously, the relation between dark matter and SUSY matter is far from being immediate. However, the fact that such a SUSY particle may also be eventually account for the non-baryonic dark matter is therefore either a big coincidence or a big hint. So people really do hope that something of that time may come out soon. It must be noted that any heavy relic particle may behave a CDM, and a host of other exotic possibilities have been suggested. Lest to become overconfident, we should remember that nature has many options for particle-generated dark matter, some of which are less costly than SUSY. SUSY is a very costly system. For every known particle, there's an unknown object to be made. It's a hell of a lot of extra stuff required to solve the dark matter problem. Of course, the dark matter problem is a major problem, so even a major solution may be acceptable. However, in order to be also the origin of dark matters, there is one problem. The lowest lying neutron particles must be able to survive 13 billion years, which is a lifetime of the universe. The dark matter particle is not only a particle, it's a stable particle. It's been around for 13 billion years. Now, how can we make the lifetime universe permitted SUSY particle is 10 to the minus 18 seconds. So what is making us to transform an object which without any specific condition, the standard kinematical lifetime could be of the order of 10 to the minus 19 seconds, how can it go and become so stable as to be able to live for 13 billion years? Now, to do that, we do what we did in the past. We need to postulate some strictly conserved quantum numbers. It's called R-symmetry, capable of almost absolute conservation, with a forbiddance factor, which is the product of these two numbers, which is something like 35 orders of magnitude. So you have to do this thing, you have to stabilize it, otherwise you will not be able to get the universe going the way you want to get it going. Now, the LHC is now going. People are looking for experimental signature, and the experimental signature for SUSY particle is generally very characteristic and is deeply affected numbers of communication other events. You can see here an example of a SUSY event. That's the example of the SUSY event. If you look at this event kinematically, you discover that this is somehow the parameters, and somebody will find this is the kind of background, And this is a kind of gigantic signal which is produced by a SUSY particle, which will be a clear signature. Now that will be the beginning of SUSY, and eventually one of those things, SUSY, may become also the reason of the, this is an example, but there can be many others, and so forth and so on. So SUSY can go extremely well from this other point. But now, another interesting question is to look for WIMPs which are as relic WIMP. I mean, of course, we can make new particles with the LHC, but we like to say that the greatest majority of matter is already there. At some level, there must be expect collisions in the laboratory between dark matter and SUSY particles. The SUSY particles in this particular class of event, relic SUSY particle, are normally called WIMP, weakly interacting massive particles. And what you observe in this case, you have here one of these hypothetic WIMP coming out. Is going to hit an ordinary nucleus, a nucleus of a detector. And then there will be interaction there associated with the W and Z coupling. And here the WIMP particle will be scattered, and the recoil, the nucleus on which you be hit, will be recoiled. Now let me tell you, the speed of the WIMP particle is not anything, it's well known. Is the speed of the galaxy, is a typical speed of a galactic material, which has a velocity of 10 to the minus 3 in beta, or something like 220,000 kilometers per second. Something like 1 million of those particles are crossing us every second per square centimeter. So it's a very hell of a large flux, and this is what it comes from numbers. And some of those can collide with our ordinary matter, maybe a xenon, maybe a semiconductor, or maybe a scintillator or whatever, and you can get a very tiny little recoil coming out. Now this recoil is in fact a recoil which is like a neutrino, and in fact the typical energy of the recoils for these numbers is somewhere between 10 and 100 kilo electron volts. So this thing will only recoil with few kilo electron volts, and of course now we have to realize that sufficiently sensitive search may also confirm or exclude the presence of such a thing. Now, there are two possibilities. Either you find them or you don't. If you don't find them, there is no electroweak coupling. It means that in the ultimate case that dark matter is only gravitationally driven, nothing of that will be there. So there is not guaranteed that you're going to win with this thing, but it's certainly worth trying. Now, the connection between the relic dark matter, the one done in the underground laboratories, and the SUSY particle from LHC are being predicted by various theorists. And you can see that according to this line here, each point represents one possible solution to the theoretical consideration. And you see that most of the possibilities are sitting in this general area here. And this corresponds to a certain rate of events. The key element in there is the mass of the WIMP particle. If the mass of the WIMP particle is SUSY, SUSY must not be too heavy, otherwise these famous three lines will not cross into a point, for instance, at the lab measurements, otherwise you will not be able to detect it. For instance, the Higgs particle would not have the right mass, and so forth and so on. The many reasons keep telling us that the convergence in the region of the order of a fraction of TeV. So this is what is the hypothesis you can have. And you can see this is the cross-section. This is about 10 to the minus 46 centimeters cross-sections. And then you can see various possibilities. Now, in terms of practical arguments, the question is how big has to be your detector and how long it has to run. And here you see, to get really down here in a very good place, you need something like one event every 100 days for something like a 30-ton detector. A 30-ton detector is a very heavy detector, especially because you have to detect only 20 kilo electron volts recoils. So take a 30 tons and ask for 20 kilovolts is not trivial. You have to do a very careful work. So the ultimate WIMP detector requires some 10 to 30 active tons and a strong rejection of cosmic neutrino backgrounds, a vast international investment. And in fact, we have a large number of people now which are working on this possibility. There is one good news, however. The good news is that neutrinos coming from, for instance, from cosmic rays, or coming from the cosmic rays, or coming from solar neutrinos, can be separated from the WIMP recoil mass, because the recoils of the recoils energy of the for instance, solar neutrinos is stopping here in a typical target to something like 15 kilovolts, and therefore leaves you all this space here available for looking for a very high sensitivity to the WIMP particles. Therefore, the WIMP particles above something like 15 kilovolts are well above the emission of recoil events from solar neutrinos, and can be, so therefore solar neutrinos and the other things can be easily separated, and this essentially therefore the neutrino background leaves open a wide rate windows of which the WIMP signal can be experimentally conducted. And there is, of course, a very large group of people which are now working on the competing on these experiments. You can see here the various experiments. You see various places: Spain, Canada, Germany, France, USA, and so forth and so on, which are working on different experiments. And you can see various types of detectors. You see almost 20 experiments which are now in action. There's a huge community of people which is now today is trying to produce those WIMPs to see whether you can get a signal from a relic particle, presumably, in competition, or if you like, in cooperation with the hopes from these things. All these experiments have given no results for the moment. None of these experiments has seen any sign of dark signal. However, there is one experiment called Dama Libra here, which has been done in CERN, which claims to have discovered something evident for the presence of WIMP particles, or some kind of particles. And this is a very simple experiment, which has been run since 1996. It's located to the Gran Sasso. There is sodium iodide crystals, low activity, and you go there, and in this particular case, you detect, as a function of time, the rate of counts. Most of the counts are background. Few counts can be a signal. And the signal should depend on the movement of the galaxy, and therefore a change of this rate may be a reason for having a signal dependence. Let me show you very briefly the result. It's quite remarkable. You see here the annual modulation, which has been done by this experiment. You can see here these recoils are a few kilo electron volt recoils in this, and you can see that this thing oscillates very precisely with the correct amplitude of the signal and with the correct timing with respect to the sun emission, and therefore you could argue that this is a mechanism to explain the presence of dark matter. Of course, the whole question is not so simple. The argument why this experiment will see dark matter is essentially coming from the fact that we have this is our solar system. This is our detector sitting there, and during the summer, the movement of the detector is going. The movement of the Earth is moving in the same direction, increasing the speed of the movement of the WIMP particles, because the galactic motion is adding to the speed of the Earth. When we are in this area here, when you are on the other side there, you find that the movement of the Earth is in opposition with the movement of the galaxy. Therefore, there is a slight Doppler shift in the speed, and this effect is producing a small change in the rate, which you observe in terms of an oscillation. Now, of course, this is December and June. You can see that for sufficient high energy in June, you have more counts than you have in December. And this should be the explanation for Dama. But this is, of course, quite a serious problem. Let me summarize the situation here. Here you see the area of this WIMP calculated by Susie. So if Susie is right, the same curve I showed you before must be somewhere in this region here. These are the standard experiments, xenon, CGMS, etc., which are observing single collision recoils. This is the experiment from Dama, which is instead observing essentially the time dependence, the yearly dependence of some rate. And if you have the area is somewhere in here, or somewhere there, depending whether you put channeling, no channeling. There's another cosent experiment which agrees with Dama. But essentially, there is a total disagreement with this story here and this story there. So how can you explain the two phenomena? What is the cause of all this? And this is really a question which is particularly important. Now, the experiment, as I said here, is essentially looking at the recoil. The experiment there is looking at time dependence. Now, the reason for this disagreement is so far essentially explained, and a lot of explanation has been introduced to explain it, but certainly at the present is an open question. Is Dhamma picking up a local nonsense, or is, and therefore there is no WIMP, or the WIMP are sitting in the SUSY area, which is completely separated from the other area, and so forth and so on. You name it, you can choose it. So a fourth question ahead of us is, Dhamma must be understood. Now, the Dhamma Libre effect has been now confirmed to a high degree of evidence, but its origin is so far wide open. Is the effect due to cosmological, as hinted by the nature of the maximum corresponding respective galactic speed variation of the solar system? Or if the effect is cosmological, is it due to electrons or recoils, because everything is in there together? If it is a cosmological effect, performing the same experiment in the southern hemisphere where summer and winter are swapped, if it's cosmological, it will be the same time-wise. It will be local, it will be changing, the summer and the winter will be changed, so you'll be able to separate the two. Is the effect persisting with material of different Z and different experimental configurations? Can the effect be enhanced in detecting directionality of observed recoils with other methods? These are all questions which are open. It's quite clear that Dhamma Libre experiment must be repeated. Let me also mention another important question about the searches, which I'd like to briefly mention to you, which is the possibility of doing experiment in space. We have a Pamela, which is an experiment nowadays running in Italy with a Russian satellite. We have AMS, which is going to be the major experiment built by Professor Samting and by a very large international corporation, including people at CERN. And this thing will be the last shuttle flight transporting into orbit, into space, a very large detector, which will detect essentially antiparticles and antimatter, and try to see whether these antiparticles could be the result of a collisions between two WIMP particles, amongst other things, between two WIMP particles, which will then annihilate in itself and go and produce antiparticles, antipositrons, or antiprotons, which may be detected in outer space. And this experiment is now, the experiments are now being carried out in both in, and they indicate the proton, antiproton and proton flux does not seem to represent any indication for WIMP effect, but the positron effect, you can see these are the prediction, these are the data, seem to show an effect. Now, it's likely that in order to be, there are other possibilities, of course, to give a positron effect, and the results put strong constraint on dark matter models. We usually do not predict asymmetry between leptonic and hadronic productions. In other words, if WIMPs are doing that, they should do for both. But we do observe one is okay, the other one is not. So maybe there are other reasons. And of course, this we are waiting for this major experiment in space, the AEMS experiment, to be able to do and to detect experimentally such a possibility. Now, since my time is getting short, I would not spend too much time to discuss other alternatives, in particular the alternative of neutrinos. And just to leave you a few more, I've been talking for 48 minutes, just to leave you a few more minutes for discussion, I would like to come quickly to somehow to the end of my presentation and leave the neutrino story to something else later on, if maybe we're going to get there. So let me come to the then to the final conclusions. Although there is a lot of very interesting physics, which I'll be delighted to talk to you, but obviously I cannot speak slowly to you so that you can understand it. I hope you understand better if I speak slowly. And at the same time, to cover all that is new in terms of physics. So let me now then skip all this story here and come down to the conclusions. Okay, just a moment. There we are, getting there. And we can have, if you have a question, we can discuss in the question. Okay, now the situation is conclusion. Here we are dealing with the subdivisions of the scientific community in two major classes. One of the class are the people which are working on the LHC, and they say, if I have a big enough accelerator, I can do everything with it. So if I want to get my next Nobel Prize, I get hold of the largest accelerator I can find, collect a few handy particles, and then go to Stockholm in due course. The second alternative is to say, but there are so many particles going around, so much dark matter, 10 times, 20 times the matter which makes what we see. And it is impossible that such a huge dark matter could not give us some signal in the sun experiment. Then in this case, you go not to the experiment, but you go underground, where you'll be quiet, though you don't have any signals. And there are many, many underground experiments now developing. There's a beautiful one being developed in the United States of America. There is a one in Gran Sasso. There are some others in various places in Japan and other places, and so forth. China is also coming up today with a very large underground experiment. We go underground, quiet place. We remove all the local background and go and see whether some of this bloody object will kick an ordinary particle and give some tiny little signal, which will tell us something which will be unmistakably detected as the cause of the presence of this huge fraction of particles, which are the dark matter object. If there are particles, it could be a classic field, or it's other things. Now, the important point there is that, in fact, this detection, these two alternatives are combining, and although there is a lot of discussion, for instance, Wilczek said only the LHC stands a real chance of breaking the existing paradigm. And in fact, nature has called it the unstoppable collider. There could be other things that other people do. It's a sort of a David and Goliath comparison. And you have one thing which you learn in elementary particle physics. Now, you're coming to elementary particle physics. It's a new story for you. So you should learn a few facts. And one of the important facts is you never know where the next discovery is going to come from. It can come for 2,000 people working together in an LHC experiment. It comes from 3 people working quietly in a laboratory with the thing, which can be portable. The truth is that the answer is not obvious, and the next step can be anywhere. And this is the great strength of unthinkable ideas or unexpected discovery, and that you cannot, if the next dimension discoveries will come from. Let's see, and there are other major subject investigation on ground and in space are competing with other sort of with each other as a sort of David and Goliath confrontation. Of course, Goliath being the LHC and David being the small, tiny experiment done in underground places. Now, the discovery of a SUSY, in my view, very speculative, in spite of the insurances of the theoretical communities. The people have been talking about so many times, SUSY particle, they now happily produce 25 Higgs, 15 extra objects, and so forth and so on in the various places. And they keep talking about it and are repeating to each other those things seem that finally they are convinced they exist. Maybe the real problem is for bonanza for the presence of a collider. Of course, that would be fantastic. That would be probably the only way you're going to get another accelerator in this world. However, in relation to dark matter, a relationship between SUSY and dark matter is not obvious or granted. And the other thing I was saying to you, likewise, the neutrino sector may reserve for us incredible new discoveries. And in proton decay, as I've shown to you, the 3 lines getting together in one point, may be in the domain of experimental discovery, opening the experimental observation on the grand unification of all forces. You remember these 3 lines going to a point I was showing you before. Events from space and underground have immense role to play in the future. Now that let's see it's the last in operation, European physics concerns should concentrate again some of the efforts and funding also to a broader range of other activities in a wider collaborative effort of the many other unthinkable ideas addressed to the experimental question for dark matter in the laboratory. Let me conclude with the following picture. Initially, when we started, man came on Earth. In the old days, we had earth, we had air, we had fire, we had water. And that was the old-fashioned shape in which the world was classified. Today, we are in fact having baryons, having neutrinos, having dark matter, dark energy, and we are doing much more complicated system, and we are doing perhaps in a different system. Indeed, the system is not at all any better because we do not know the identity of 95% of what is making our universe. And this is a tremendous challenge and a tremendous discovery potential for all of you, especially for you young people who are coming into the field. Thank you very much. So we have time for a few questions. If you don't mind, we can have a few questions.
Yep.
Just briefly. Yes, sir.
Okay, there is one there.
When you introduce SUSY, you actually double all the particles. So every SUSY particle should have a SUSY antiparticle. How do you solve the problem that they do not annihilate like matter and antimatter? Is this?
No, it's not that. The difference is between fermions and boson. The SUSY particle and the other, particle and antiparticle annihilate if they're the same. The protons annihilate with the antiproton, the electron annihilates with the positron. But atoms, which are made of an electron and a proton, do not annihilate with each other. If you had to put a positron, they will not annihilate either. Annihilation requires a very intimate connection, which is only possible, like in biology, only if you belong to the same family. SUSY particle and ordinary particle belong to a different family. So the SUSY particle are characterized by the fact they have different masses, different characteristics, but they're under the fundamental exchange to be fermions or to be bosons. For instance, we have that most of the electrons, for instance, are fermions. Do electrons don't say the same thing, Pauli principle, etc., etc. This electron, the superconducting electron, will be instead a boson. It will be like a pion. It will be a particle which will have essentially no spin and so forth. So they are really different particles. They're coming from the fact that some very reasonable theoretical consideration tell us that perhaps there is a basic symmetry between being a boson or being a fermion, that you can have one and the other together. This is coming up essentially from the fact that at very early times, very high masses, when gravitational, at the Planck mass, at that moment there, you could have, this situation could be ambiguous, not broken anymore. And therefore, you will develop two different lines. Now, they hope that there is a supersymmetric particle at our mass, not at the mass of grand unified theory, is something which is an hypothesis which has to be tested experimentally. But it is that SUSY particles are different than particle because one is fermion, the other is boson, and vice versa. So they are different particles, they don't mix with each other. However, the lightest supersymmetric particle may be stable because he will have, this is the neutrino that we're talking about.
I think there was another question there. Oh, no. Okay, one on the back.
There's one in. Shout.
I have a question about the Dharma data.
Yes?
You showed that there's a fluctuation between winter and summer. So how can you be sure that the fluctuation doesn't depend on the distance to the sun?
This distance?
To the sun.
Be careful. I mean, in our hemisphere, we are, the distance between the sun and the earth is the opposite of what you think. During the summer, we are further out to the sun than the system. This is a small effect. But here we are talking about something different. We're discussing about the fact that the sun moves with a certain speed, a few kilometers per second, but then the dark matter should in principle be independent of ordinary matter, and therefore the typical galactic speed should be valid independently for matter, for dark matter and ordinary particles. You've seen in that picture when these two things collide, they do keep themselves quite separate from each other. And therefore you would expect that the kind of wind coming from dark particles will be of the order of magnitude of the typical galactic speed, the speed by which the center of the galaxy moves with respect to the sun. And the speed by which the center of the galaxy moves with respect to the sun is about 220,000 kilometers per second. It's a relative large beta. It's beta equal 0.3. So the movement of the solar system with respect to the galaxy, center of the galaxy, is much bigger than the speed of the Earth with respect to the position of the sun, because of the fact that the system is much wider. So that is the dominant effect that you observe. In the dominant effect, you have that the speed of the wind from the galaxy is always going with a certain speed, but when the sun moves towards the galaxy, the two speeds add. When the sun goes away from the galaxy, the two speeds in the experiment on Earth subtract, and that could make a small little change, a few percent, in the rate in which you observe events, whatever they are, those events. The problem is that those events don't look like to be the events which you observe by single evident collision with the wind particles. In this case, you take everything, any kind of form of phenomenon is possible. Now, of course, the danger is that this is not due to the galactic effect. There's nothing written galactic in anywhere there. It's your decision, or Dama's feeling, that is the galaxy which is doing it. It could may well be that this is due, for instance, to the fact that during the summertime, in the wintertime, the amount of snow or the amount of water or whatever you want on your laboratory is different because you are under a mountain, and the mountain during the summer moves with respect to the summer moves with respect to the winter. For instance, you have snow in one case and no snow in the other case. When you put snow, you increase the thickness. If you increase the thickness, you reduce the amount of cosmic rays. If you reduce the number of cosmic rays, you get less signal. So it could also be that. But they have carefully looked at all those things, and they claim they understand this and that and the other because of other circumstantial evidence. So they throw everything out, every possible idea out, and the only thing they say is there is Dhamma, is the galactic effect. But then you should see some of those wimps bumping into your experiment and give you recoils. And many other experiments are doing that. On xenon, on argon, on semiconductor detectors, on cryogenic detectors, people are looking for these 10, 20, 30 kilo electron volts recoils. The heavy recoils, very difficult to measure. They're very low in energy, but sometimes they should develop themselves. And they are sufficiently characteristic that you can separate them out from neutrinos. And don't see them. And there are many orders of magnitude difference. But of course, nature may also have a solution in which why you don't see something, you may see some others. But obviously, I'm telling you things which are not part of the books of physics. I'm giving you real-time physics. So in 2 years from now, maybe the whole thing will change. So therefore, you should look at this phenomena as hints for something, not something as a proof. Okay? Yes, sir.
Microphone coming.
Thanks. I would like to ask, what is the reason of stability of neutralinos?
For what?
Stability of neutralinos.
Well, good question. It's a hell of stability you need, because anything you do with those, the top particle, for instance, stays there 10 to minus 18 seconds and it goes away. W particles, Z particles, just energy is plenty, and so stability has to be done properly. Now, there are some theoretical ideas. I'm not a theorist, so don't blame me for that, which says that there is so-called R symmetry, which is a symmetry property, which is related to the fact which the other fellow was asking before of being a fermion or being a boson, this kind of, in this chapter, which says that R symmetry should be there, Certainly in some theory, you get lots of hints of that. But the problem is that theories are one thing, and nature is another. And here you need 35 orders of magnitude to kill in order to go to something which is stable on 13 billion years compared to what will be the stability of a SUSY particle when, if you're going to find it at CERN. If you find the SUSY particle at CERN, somebody said to you, hey, how can you get that bloody thing stable 13 billion years? And this is 35 orders of magnitude. Now, of course, there are laws in physics which are correct within huge number of dimensions or sizes. For instance, gauge symmetry, it's something absolutely stable. The zero mass of, etc. But there are some fundamental law behind it, which tells you that the photon is zero mass, etc., 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 etc. I mean, this kind of explaining is not yet there for the point of view of stabilizing the lightest particle to the extent of being able to live such a fantastic amount of time. But you cannot exclude it. So, I mean, the question is, it's great. You know, anything is possible. I said to you, you can do it. Or, you know, some people are surviving their idea by saying there is an R symmetry, which causes it. Some others say, well, what is R symmetry? I say myself also, what is R symmetry? I never understood myself very well what it is. But maybe it is there. We don't know. We have to find out. There was another question here. Yes. Oh, finally we got a girl. Very good.
Thanks. I was wondering, with respect to dark matter candidates, whether you could comment on the importance, in your opinion, of searches for axions, and whether you think there are the same problems with PQ symmetry as there might be with R symmetry.
Well, let me say the following. I am convinced that we just don't know. We don't know anything. I mean, we now have built in the last 5 or 6 years evidence that dark matter exists. And this is coming essentially from the Kobe experiment, which has given the last Nobel Prize to people which have observed the effect of Kobe, and so mass, etc. And we have demonstrated beautifully these results. So, cosmologically, as I said at the beginning, dark matter is a must. I mean, at the present moment, if you put all the evidence together, you say, I can feel content with it, and I'm convinced that we have something. But now, as I said at the beginning, it can either be purely gravitational period, and in this case, you will not be able to see anything. So it may well be that we are going to go for 20 years of progressively more and more complicated and expensive experiments, and we'll find no SUSY particles, we'll find no relic events, no axions, no nothing of this type, no possible alternative in the system, because there is no coupling, because the key element is the coupling with the W and Z, because those things are completely sterile, they don't interact with each other. It could well be that, hypothetically, the dark matter is like dark energy. If we know nothing about dark energy, maybe dark energy is something like, which has to do with classical fields. I mean, the gravitons don't exist. The gravitation is a classical model, and so it may well be that we are just saying only people looking at distant stars with gravitational lensing will be able to tell us something more about dark mass. Well, for us, we will know it's there, but we'll know how to get it experimentally in the laboratory. We so far have thought that any experiment needs ultimately to be measured in the laboratory. You need to have your gadget and see the effect is there, reproduce it, make it work, etc. And this means the equivalent to that is we have now to find out where dark matter can be detected in experiment. But it's not obvious that we'll find it. It's not obvious that any of the 25,000 alternatives that people put in there is valid. It may well be that this, in reality, this is only gravitation, period, punct, it's finished, end of the story. But we don't know until we have tried. I will find very strange if we will not be able to see any coupling between ordinary matter and dark matter to the point that under no circumstances one will talk to the other. you cannot, it's hard to imagine that you have 96% of the universe not talking in any possible way except gravitation with the remaining 4%. So things like axions or WIMPs or all the other elements you have there, you name it, and so forth, are probably But this is at the present moment it's a mystery. It's a story like you know, the ones in the police in the criminal stories. I mean, you know, you don't know who is the murderer. And so like this movie, Murder on the Nile, except here we are doing something different. But it is something which is very exciting because it is also a poetic touch, a curiosity touch, as I said at the beginning. You don't know where the bloody thing is going to come out. You may not need to build the most expensive result to get the hint, that hint that you want to have. You may do something simpler. Because in the axions, you can do much simpler experiments. And we are all in a democratic situation. There will be a winner amongst you, but you don't know at the present moment which one will be the one.
We have still time for one last question. There is one here then.
My question is about one of the last slides about the speculative nature of supersymmetry. That you think that theoreticians pay too much attention to this supersymmetry concept. Well, it is a question. And would you bet any money on the existence of supersymmetry? How likely is it?
Well, let me try
because I mean, a lot of people have bet their careers on it. But so, how much money would you bet?
Well, let me say, I think CERN has bet 5 billion euros out of LHC. And you know that one of the dreams is to get supersymmetry. Professor Ting spent 2.5 billion euro in constructing a EMS experiment, which you go to the space shuttle and try to see something else, some other phenomenon of dark matter. So the amount of money that one is putting together in science is quite substantial. And the time is very long. I mean, let me tell you, the first time we invented the word LHC was 30 years ago. It took 30 years. Most of you people were not even born when we invented the idea of LHC. And so, I mean, it takes time, it takes effort, it takes resources. There is no... usually, nature is much more clever than we thought. I mean, think, for instance, the case of Einstein talking about the lambda zero. You know what lambda zero is. You know omega lambda, what it is the fact that the dark energy is there. The dark energy was described by Einstein in its original equation. Omega lambda was described by Einstein in early 1920. And then he got Einstein got himself extremely upset by this. And he said the famous phrase, "This is my biggest blunder." And now, so he threw it away, saying, "Is it not possible nature to be so stupid to do a thing like this?" And now we have two experiments which have been performed a few years ago, in which we have measured the presence of a dark energy, and we have experimentally demonstrated that dark energy exists, exactly what Einstein did not have the courage to manifest itself on. So there is evidence that surprises are possible, and that nature is normally deciding things in a way much more simply and much more cleanly, that whichever person can hypothesize, and I'm not talking about anybody, I'm talking about Einstein, which is not a trivial person to criticize about. There's one important thing which is happening now. Cosmology and elementary particle physics are become, from a philosophical statement, an experimental fact. For many years, the Big Bang was considered to be a result belonging to the past, to the history, to the philosophy, to whatever you want. There was nothing there which you could still say about the Big Bang. But in reality, today, we can measure the Big Bang like we measure anything. And we can put numbers on this. We can put numbers, we can do measurements, we can say this was it. And we can find out all kinds of different things. For instance, we can find we have weighted the universe. We see how heavy is the universe. Omega 0 equal 1 is the weight, is the mass of the universe. We can measure it with 2% accuracy, 2% accuracy today. So cosmology is becoming from a philosophical, if you like, metaphysical principle, idea, which, by the way, they're also perfectly legitimate ideas, but they don't belong to the natural philosophy, to a purely natural philosophy idea. And the most important thing which happens, both in elementary particle physics and in astrophysics, together in astroparticles, it's astroparticle becomes something on which you can today either simulations with accelerators or observations by looking at a variety of things here and there in the outside universe and so forth. You can come up with some kind of a perfect scientifically, experimentally demonstration of this fact. So now we are going from a sort of a metaphysical consideration down to a practical experimental result. And now, at the present moment, much more in the future, we are going to find that those questions which are highly hypothetical become real things which can be tested. And of course, theorists are producing a large number of alternatives. They should do so. I think it's an excellent idea. But in the long run, I mean, you cannot have, even theorists many times have theories which says one thing and the opposite. But it cannot be in nature either the thing and the opposite. You have to be one or the other. So theorists are precursory statements to the real facts, but I personally believe the ultimate answer will come from the experiment, which will demonstrate to us that those things are real, they exist, they are measurable, they are characterized by certain type of results, which are becoming a part of our culture, our knowledge, and so forth and so on. For instance, if we were to discover the dark matter is there in an experimental way, this is a result of an immense dimension. Is something like the time in which people suddenly realized that the Earth was not the center of the universe. Remember, the Ptolemaic system was saying the Earth is the center of everything. Now we say ordinary matter, standard model, is the presence of everything. And here we have the statement that realizes that today we believe that the Earth is just our system is just one little thing out of a tremendously complicated system. We are a footnote of a much bigger situation, a much bigger system. It is a very major change in concept, which not only has significance in terms of physics, theoretical physics, experimental physics, but has also something to do which have to do with all kinds of forms of culture. Similar situations happened at the time in which when we discovered that Darwin discovered that the man was just simply a monkey with a triple A in front of it, and there was the evolution of species. That was another major discovery forward. Now, if we were to come here, if this is mostly your job more than mine, because it's your age which will be the heart of the system, that dark matter is the dominant form of the universe, and we are a footnote because we only have a few % of it. All we see, we know, is just a footnote. It is another thing which will not modify only your own curiosity, or this. It will be something which will have very deep consequences, which will go out from a simple experimental result into the way in which we perceive the world around us. And therefore, we are in the present moment in front of a major new development, which I think deserves, if it works out in one way or the other, the conclusion of which will be very lasting for the future of the work which we are now starting today to carry out.
Thank you very much.
So you wouldn't bet.
What?
So you wouldn't bet.
Those things are not worth betting. Those two things are not worth betting. I think, in my way, I learn a lot of things from. You see, I have one advantage that I lived through physics in a variety of ways. Most of the things which today exist were not there when I had your age, when I was a student. I have not seen many of the things which you laser didn't exist. Various things did not exist. I mean, superconductivity was still not understood and so forth. I mean, there was a tremendous, in every field, there was a tremendous development. So I would say honestly, 70% of what I know now was not learned by going to school, but was learned by just watching it to happen. And in this process of watching it to happen, the situation is entirely different than the situation of finding it in the book. We are reading physics in the books. We are missing one point. We are missing all the richness of the discovery, all the richness of not knowing what it is. The large number of people which have invented something which was completely wrong, and some other person which comes something which was perfectly right. And the way in which you are going step by step, going from one situation to another, as a part of your living experience, it's an entirely different feeling than the one of just going and taking a book and going learning, as you do at school, the science or physics in particular, in a literary way. Because that is killing completely the mechanism of evolution and the pleasure of seeing how hard it is to come up with a new discovery and how different the new discovery is than what you thought in the first place to be. You are assuming that, page 1 says that, page 2 says that, but they don't tell you what is in between the lines. And what is in between the lines, in my view, is really the best thing. And I'm sure that if you get into physics and enjoy that, after a while you'll say, but I was there, and when I discovered that thing, I mean, LHC wasn't even there, wasn't working and so forth, and now we have these results and so forth. It's a different way of getting into the understanding than just finding it from a book. Okay. Well, we are going very far here. We should close down. Huh?
I think we can really thank Professor
Thank you.
Carlo
It's a
Rubial
pleasure.
for this
Thank you very much.
enlightening question.
Fine. So let's go.